a little bit more about Bolzano. He started his contribution to logic, and here I'll go a little bit fast, but it's all in the slides. You could, if you read it carefully. His idea was that you could use sort of the idea of Gödelization, the idea of applying truth statements in the theory to statements in the theory itself, actually goes back to Bolzano. Sort of what he does, for example, this is his proof that there is at least one true proposition. Okay, we write first, there are no true propositions. It's a proposition, yes? Then we observe that if first proposition is true, then it's false. Then we observe that it is false. Then we observe that the previous thing is true. Then we observe there is at least one true proposition. All right? Sort of, this is, and you say, well, this is sophistry. Yes, but so is the work of Gödel, in a sense. Applying your thing to itself, it's a bit sophistical. And we'll study it to greater depth, but sort of the first idea, well, it's not quite true. Again, there was some amazing work in 14th century, which I will refer to in the next lecture, if I ever get to the next lecture. So he sort of builds that, and this is a problem for you. Using Bolzano method, prove that there are infinitely many true propositions. It's not difficult, and he does. Sadly enough, his magnum opus, which is 3 huge volumes, is translated about maybe 15%. University of California Publishing House came up with a very nice book, but it's an abridgment. So most of his work is still not studied. And this is one of the cases where, it's not clear when it will be studied. His complete works, I think, are reaching something like 60, 70 volumes. They're still in preparation. So lots of stuff he wrote. And here we need to jump to the final person, the person where you expected I would start. But I didn't start with him. I started before. Georg Cantor, a complicated, tragic figure, never could figure out who he was in many respects. You see, he didn't know even whether he was German, because he was born in St. Petersburg. That's in Russia, like Ilia. But Ilia doesn't have any self-identity problem. Cantor did. Sort of, he never knew sort of whether he was German or Russian or maybe Danish, because his father moved to St. Petersburg from Denmark during Napoleonic times. He didn't quite know what his origin was because he was from a Lutheran family. But Cantor, Lutheran? Maybe not. Sort of there are strong, again, Jewish Encyclopedia says he was Jewish or Jewish descent. Was he? It's not very clear. But on the other hand, in his letters appear very strange remarks, sort of statements like, oh, I hate being with Jews, which would indicate that he sort of viewed Jews as his relatives. This is sort of not a simple thing. And then, of course, his great nemesis was the most prominent German mathematician of, as they used to say, Hebrew descent. Leopold Kronecker, the head of mathematics at Berlin, sort of an enormous figure, very important, who would say that we have to protect youth against the deviations of Cantor. Sort of when the most powerful mathematician starts saying things like that about you, you don't feel very good. So he doesn't quite know what he is. Very insecure. Sort of doesn't even trust his friends. Sort of never gets an appointment which he wants because he wants to be in Berlin, but Kronecker is in Berlin, and Kronecker over his dead body. And even after he dies, Cantor doesn't get there. So he starts with good works on analysis. He doesn't start with set theory. But then he starts getting this urge. As he says in his letters, he has a sort of, he hears the voice of God. There's very strong mystical things. Sort of he always insists that he didn't invent it himself. It was a sort of revelation that he started dealing with things. Eventually, he meets Dedekind, and they become friends. Dedekind is older, and Dedekind always helps young scientists. And this is my sort of summarization of letters between Cantor and Dedekind. So the first Cantor writes to Dedekind in a letter, long letter, but summary. Could we enumerate positive real numbers? Dedekind, that's an idiotic question. Nobody cares. But, by the way, this is very interesting. He sort of says, nobody cares about things like that. But then he writes a long proof, which I'll tell you, that we could enumerate the algebraic numbers. I'll tell you what algebraic numbers. So Dedekind doesn't quite know, and it's quite, honestly, he doesn't quite know whether it leads anyplace. He uses sets because he sort of at that time thinks how to define real numbers. And you know, some of you might know about Dedekind cuts. They're sort of based on notion of sets, but the notion of one-to-one correspondence does not appear to be important. So he doesn't think it's an interesting question. But then Cantor writes in a letter, then if the answer to my question is no, that we could enumerate positive real numbers, then it will prove the existence of transcendental numbers. Because if we could enumerate algebraic numbers but cannot enumerate real numbers, then there are real numbers which are not algebraic. Make sense? That's what he says. We'll have an existence of transcendental numbers. Again, transcendental number, a number which is not a root of any polynomial with integer coefficients. And it was an outstanding problem to prove the existence of transcendental numbers. It's actually solved a while back by Louisville, who shows that certain numbers, and Hermite is just going to prove the next day, sort of, that E is not algebraic. And Lindemeyer is going to prove that using Hermite's proof that pi is not algebraic. So Cantor writes a letter saying it's an interesting question. If you actually want to know, it will tell us. And then Cantor says this emphatically, the answer is no. I proved that we could not have a correspondence. And of course, at this point, you say, oh, he invented diagonalization, for those of you who know. No, he actually didn't. He came up with a very beautiful and totally different proof of a very different nature. So let us, I think that if you learn it, it will do good for you. It's a wonderful proof. It's a little bit complicated, but let's try to do it. So this is, well, here I need to talk to you about Hilberts Hotel. You know about Hilberts Hotel? I'll tell for those people who don't know. So there is this notion of countable sets. And at some point much later, Hilbert, to illustrate the notion of how strange infinite sets are, came with the notion of Hilberts Hotel. Hilberts Hotel is a hotel which has infinitely many, countably many rooms. And they're numbered 1, 2, 3, 4, 5. And it's full. In every room, somebody stays. Well, somebody comes. Is it a big problem? No. We could always find a room. How? We move the guy number 1 to 2, 2 to 3. There's one room. What if 20 guys come? No problem. We could move the guy number 1 to number 6. Every guy number I will move to I plus 5. And did I say 5? 20. OK, make it 20. We move, and there are 20 rooms. So, good. What if infinitely many guys come? Just infinitely many guys want to stay in our hotel. No problem. We say, you go to the room 2I. And all the odd number rooms are free. And how many? Infinitely many. What if infinitely many buses with infinitely many, countably many people come? No problem. We could put them in the hotel and have lots of room empty. How do we do it? Well, for every guy, we say, go to the room 2 to the I. That means that the original inhabitants or whatever, clients, go to power of 2 thing. Then for every bus, we say, for the first bus, we say, you go to 3 to the I, the next guy goes to 5 to the I, the next guy goes to 7 to the I, and so on. And we have infinitely many rooms with nobody, like 6. Right? So the amazing fact is that, this is known as Hilberts Hotel, which shows you that there are one-to-one correspondences between one countable set and 2 countable sets and whatever. It doesn't work in real life. Just an important thing to remember. Counting rational numbers. Apparently, the idea was at first, they thought that you couldn't count dense things. Things with no gaps. Between any 2 rationals, there is at least one more rational. Well, actually, infinitely many rationals. Well, apparently, you could count them. You could count 1. This is how you count them. Third, so we could count rationals. And here, let us count algebraic numbers. This is my abridgment of Dedekind's proof, usually referred to as Cantor's proof. Cantor published it, but it was suggested to him by Dedekind. By the way, just a trivia question. Who edited and published the correspondence between Cantor and Dedekind? I mean, you know the name, but you could not possibly guess. Amy Noether, yes. Sort of. There is this, it's a small world. So let us look, first of all, let's define algebraic number. An algebraic number is a root of a polynomial with integer coefficients. X squared minus 2 is equal 0. Right? Therefore, square root of 2 is an algebraic number. Right? Now, we define polynomial has weight k if k is the maximum of absolute value of its coefficients and exponents. There is a maximum. Now, I claim there is only finite number of polynomials for any given weight. And every polynomial has a finite number of roots. So we have countably many finite sets. Could we enumerate them? Yeah. We go through enumerate for weight 1, weight 2, and so on. We enumerate all algebraic numbers. Right? It requires, you need to write it all up, but you get the idea. Now, here we come to a non-trivial thing, which is not known by many people, but It's absolutely a wonderful thing to know. This is Cantor's original proof of the fact that reals are not countable. That continuum, the line, is in some sense bigger than countable set. In what sense? Again, we shall see. Life is very complicated, so don't quite believe everything you hear. But the proof is correct, it is constructive, and it is quite wonderful. So let's read the theorem as it states. Given a closed interval of real numbers, that's the interval, A0 to A1, interval, and a sequence of real numbers, countable sequence. The interval contains a number that is not in the sequence. That means that you cannot enumerate the interval, because if you could, you will enumerate everybody in the interval. Cannot be done. Right? And the proof is algorithmic, but it's tricky. So just brace yourself. It's going to be real mathematics for just a short time, but likable mathematics. So we take our interval and we start running through our sequence till we find someone who is inside the interval. If we don't, we're done. Do you agree that if we don't, we're done? Because we went through all the sequence, none of them are inside the interval. So there's somebody inside the interval who is not in the sequence. Yes? So we start running. We find the first guy. We will call him A1. And we'll keep going till we find B1, which is greater than A1 and also in the interval. Again, if we don't, we're done. The same argument. There will be an interval from A1 to B0, which contains lots of elements not in the sequence. We agree? So now we replaced A0 with A1, and we keep going. We do the same process. We sort of keep running. It's a while loop. So that we keep going. We stop when they're inside and replace. I'm sure most of you could write the code. Right? I mean, you could write the code. It's literally can be done because somebody did. There is a person who wrote a program which generates, integer by integer, a transcendental number using a sequence of algebraic numbers. So, I mean, it's actually was done. So we keep going. So we're constructing these nested intervals. Right? A1, B1 is inside A0, B0. Do you agree? By construction. And so on. Okay? Now, if the sequence is finite, that is, we run out of it, then we're done. Let's take the infinite sequence. Now, we know that the infinite sequence of closed intervals has an intersection. If you don't know, we will talk about it, and it's also going to be a problem for you. But, okay, so let us take this intersection. It contains at least one point. This point in the intersection is inside every interval. Therefore, it's outside the sequence. Because it's trivial to see the following, that for every interval A sub I, B sub I, R sub i's before are not in it. It's the Littlewood paradox. I mean, we eventually get past every I if there isn't, because, you know, we know that we examine everyone and try to put it. If he is, every R sub I was either chosen or rejected. If it were chosen, it was chosen for an interval before A sub I interval, because you need 2 points for every interval. Right? So we have every element in the sequence being outside the intersection. Therefore, the intersection is not in the sequence. Okay? Now, for those of you here, the difficulty is the formal proof that intersection is not empty is a little technical. Let me, first of all, tell you that it's your homework. But then I'll tell, for those of you who remember what real numbers are, that is, the people who remember Dedekind cuts, give you a proof. So this, if you don't understand, that's perfectly all right. You see, we take all A sub i's, they're all bounded by every B sub I. So we have a partition of reals, right? And there is, by definition of reals, an element which sort of partitions smaller and bigger elements, right? This is definition of real numbers. So we pick that one. That's why it exists. But you have to think about it. I wanted to talk about Dedekind cuts, but chickened out. Okay. So now we know, and this was this remarkable discovery that there are multiple kinds of infinities. They're not just countable infinities, things like integers, but they're also continuum kind of infinity. So, and Cantor, which clearly shows his deep Hebrew roots, was the first mathematician who introduced Hebrew letters in mathematics. Nobody prior to him would use Hebrew letters. Greek, yes. Latin, yes. But never Hebrew. And then suddenly comes this notion of Aleph 0. This is Aleph, the first letter of Hebrew alphabet, and it designates the cardinality, the size, the power, if you like, of countable sets, 1, 2, 3, 4, 5. And then R has cardinality. This is Gothic C. So he was not consistent. This is not Hebrew. But there will be some other Hebrew letters before we're done. He knew at least 2. We do not know if he knew 3. But 2 kinds of infinities. So he publishes this stuff, and reaction is, you cannot imagine. Most people say, the guy is just mad. And he's, corrupter of youth was used by Kronecker. So the reaction is just unbelievable, that this is nonsense. It makes no sense whatsoever. These are not things you could even fathom about. I mean, what does it mean? Serious people. Serious people. How serious? Well, Poincaré claimed that set theory needs to be thrown out of mathematics. That is, there were very, very great mathematicians totally opposed to it. Sort of it takes time for crazy ideas to become universally accepted. And in this particular case, again, it's not clear if the battle is over, at least not to me. So there are multiple things. Yes?
You said set theory, not, so was the set theory as a whole or just the notion of infinite sets?
Well, set theory without infinite sets is not a theory. Yes? I mean, well, I mean, you don't have any results to speak of. Right? Sort of, and from Cantor's point of view, he didn't care about finite sets. He invented his great, okay, let me tell you a little bit more. Sort of he starts he's desperate. He tries to find friends. He has a very good friend, Dedekind, but eventually he stops talking to him because Dedekind doesn't want to move to his university, so he's not really a supporter. He sort of, Mitaglifler, a Swedish mathematician, starts publishing Cantor's paper in his journal. And he becomes good friend, but then Mitaglifler doesn't want to publish some paper because nobody will understand it. Mitaglifler becomes his worst enemy. Sort of, some point he decides the entire mathematical community is against him. He starts writing letters to theologians, first Lutheran theologians, then Catholic theologians. He starts correspondence with Cardinal Francelin, one of the great Catholic theologians, who tells him that, no, just go away. Then, what would you do if Cardinal tells you to go away? Whom would you write? To the Pope. Yes, that's what he does. He starts writing a letter to Leo XIII at that time. The Pope, who is a great intellectual, sort of supports all kinds of things, but apparently has no interest in set theory. Of course, Cantor says that, look, finally, we have mathematical proof that God exists, because I proved that infinities are real. Well, so he gets to the sort of really strange state. And then he says, well, mathematicians are totally bad, and the Pope doesn't listen to me. I'll go and do literature studies. That's something that Jonathan will appreciate. He decides to go and study Shakespeare and writes a monumental monograph that Shakespeare didn't write Shakespeare, but Francis Bacon wrote all of Shakespeare. And lo and behold, people laugh. So he just cannot, he's not very happy camper. And he's, of course, mentally unbalanced and goes into depressive states. Great man, but clearly not a simple case, but he's dealing with very non-simple realities. So after a while, he starts rethinking. After his Baconian fiasco, he goes back to set theory. And he discovers another central thing of modern set theory. Well, this is where you talk. Since there are more real numbers than algebraic numbers, there are transcendental numbers. So there are another thing. Sort of, he also starts, and many people follow this consideration of measuring the sets. And he comes with a notion of a measure. Well, it was actually people like Borel and Lebesgue who did, but it all was prefigured in the work of Cantor. Sort of that countable sets are very small. What does it mean? You see, if we take real numbers and we could sum their subset, we could measure the subset like following. We will find coverage of it, that every element is covered by something, by an interval. And if we could drive the coverage down, say, to 5, that's the measure, if we could have a descending sequence. So he says, let's take algebraic numbers. They're all over the place. They're more than rationals. But however, they're not just that. Countable sets are very small. If we take the union of the interval starting from a sub I minus epsilon divided by 2 to the I plus 2 to a sub I, we're just taking it, this thing on both sides. When we add them all, they marvelously add to epsilon. So we could cover with this all the algebraic numbers with total intervals of size epsilon, but we could make epsilon however small. Therefore, the measure of algebraic number of any countable set, for that matter, is 0. Right? There is, Okay. So, and then Cantor decides again, from about the time of his proof till about 1890, everybody knows that there are two kinds of infinity: countable infinity and real continuum infinity. Are there other infinities? And then Cantor proves his remarkable theorem. This is okay. By the way, the notion, the way we write the notion of a power set, we write it as 2 to the s. This is just a notation. And what does it mean? It means that x is an element of the power set if it is a subset of the set. And why do we use this notation? Because of the following simple fact. It works for finite sets. If you have n elements, how many subsets? 2 to the n. There are 4 subsets of 2 elements. Empty, first element, second element, both elements. Right? So this is why we're extending this notion of a power set by writing to the infinite sets. But what does it mean? How many other? And then, of course, Cantor observes that for countable sets, there is a one-to-one correspondence between a subset and a sequence of zeros and ones. The idea is very simple, that every subset of integers could be put into one-to-one correspondence with a sequence of 0 and 1s. Right? Namely, we put 0 for every integer which is not in the subset, and 1 for every integer which is in it. For example, if we take a subset called odd numbers, it goes 0, 1, 0, 1, 0, 1, 0, and so on. Right? I mean, it used to be difficult, but now everybody is used to binary numbers, so it's easy. So, which shows, in some sense, that the set of, there should be a slide. Yes, there's a slide here. I forgot. Okay. So let us prove the following thing, that the cardinality, this absolute value means cardinality, the size of power set of integers, aleph 0, is equal to the cardinality of the continuum. This is a very, very important, nice thing. First of all, we know that cardinality of real numbers is equal to the cardinality of positive real numbers. Why? Because we take a function called natural log. It maps positive numbers to all the numbers, 1 to 1. Remember the graph? Right. Now, let us now prove that the cardinality of 0, 1 open interval is equal to cardinality of positive real numbers. Well, again, let's take a function 1 over x minus 1. It just maps it. Now, let us map cardinality of real numbers from 0 to 1 open interval to sequences of zeros and ones. 0 and 1s interval is the same cardinality in sequence 0 and 1. Well, the proof is very simple. We could represent these guys in binary. Why do I put question mark? There's some tricky thing which you have to deal if you want to be absolutely certain, because you see 0 or, okay, 0.1 is equivalent to 0.01111111. It's the same as with names. You could deal with it because there's only countably many things with like that. So you could easily handle that. And then finally, sequences of 0 and 1s give you characteristic vector for all the subsets. So I actually don't play. It's fairly rigorous proof. And I put a question mark where you need to put additional work. Okay? So now we know that power set of integers brings us to real numbers. Are there other infinities? First of all, the problem which Cantor tried to prove, and which again didn't make him happy, there's a deeply unhappy man, and then he tries to come up with a trivial proof that there is nothing between these two things. It's known as continuum hypothesis. Well, he failed. We shall see there are profound reasons why he failed. So that is, there are no, you see, Aleph 1 means next cardinality after Aleph 0. But is it the same as continuum? We do not know. Well, we will talk about it. So, history of continuum hypothesis. This is continuum hypothesis. Right? So it's history. Cantor states it. And he thinks he can prove it. He cannot prove it. Then David Hilbert makes it famous because in his list of 23 problems, he makes it number 1, the most important problem. Now, I'm going to use some words which will be explained by the end of the lecture. Kurt Gödel shows that you cannot disprove it in either ZF or ZFC, meaning Zermelo-Frankel or Zermelo-Frankel with axioms of choice. You will know what it means. And then finally, the so-called the greatest work in logic, Paul Cohen, proves that you cannot prove it in ZF. Why it's the greatest work in logic? Because you see, no logician ever got Fields Medal. With one exception, Paul Cohen. Well, let me tell you even stronger. I mean, Kurt Gödel couldn't get a 10-year at Princeton. No chance. He didn't publish enough. He was an Institute of Advanced Studies, but never the member of the faculty. But this is just ridiculous, of course. But so Paul Cohen, who was our neighbor, he died relatively recently, 5 years ago. He was a professor at Stanford who came up with this wonderful technique called forcing to show that continuum hypothesis cannot be proven. However, Cohen believed it to be false. Right? Sort of, that is in one of his later papers, he says, well, sets are so rich we cannot believe that there is nothing in between, sort of like that. So it's not clear what we know. In a sense, sort of, all of this stuff is much less certain than people think. Okay? And it's not clear that Hilbert would be happy if you told him, well, the problem is settled. That is, it's not the last word. What's the last word? I don't know. I don't have the last word. But this is an interesting thing, and again, it ends up right across the street here. The last great result was done by Paul Cohen. So now just a reminder, a surjective function, otherwise known as an onto function, is a function from set x to set y such that everybody in y is covered. Right? I need the definition because there is a remarkable theorem Cantor proved. After many years, he proves that you could never have onto function from a set to its power set of all its subsets. That in some sense, the cardinality of a power set, a set of subsets, is always properly stronger. You cannot cover every subset with an element. Which, before we prove it, the proof is actually, believe it or not, utterly elementary. It's not as pretty as the previous one. But which gives us infinity of infinite cardinalities, because you have countable sets and power set of countable sets and power set of countable sets, and and it goes on forever, for whatever it means. Again, so let us see. This is diagonalization proof, and let us see how it goes. We assume the contrary. This is proved by continuum. We assume the contrary, that there exists a set S and a surjection F such that it covers all the elements of power sets, that covers completely. All right? Now, let us take a subset D of our set such that for any x in D, well, such that x is not in its image. You know, every x goes into subset. So we could check, is x itself in the subset? It's either is or is not, excluded middle. So we take all the guys who are not in their image. It's a subset. We will, so D is a subset of S, right? So D is an element of power set. Everybody agrees? By definition of the power set. Now, F is surjective. Is it surjective? Yes, we wrote it, surjective. That's the assumption, which implies that there exists D, such small d, such that f of d is equal big D, yes? By the definition of surjective. Now, D is in D by what we just wrote. And D is not in D by definition of D. Because it's okay. Let us just, sorry. This is true. It's either in D or not in D. Let's assume it is in D. Then it is not in D by definition of D. That only those guys are in D, this is the definition, which are not f of x. D is f, which implies not D is in D. And the other way. Meaning, contradiction. You cannot, just whichever way you go, you get a contradiction. You have to look at it and look at it. There is no depth in it, but it's tricky. Again, it's one of the paradoxical statements. Right? So you cannot have this thing. And this proof, of course, made Cantor very, very proud and made mathematicians very, very excited. But very soon it will lead to disastrous things. We shall see. And good things. So now you have infinity of infinities. Right? This, and so on. Now, if we designate the ith element as Beth, this is the second Hebrew letter which appears in set theory, Beth. And we use a limit operator. We take the union of all bets. Then it goes beyond this sequence, because it's more powerful than any element in the sequence. Right? So we could go to unreachable, just shows how we could, and now we could start doing this operation. So we get this hierarchy of unreachable, so what do they are? They are. So again, you have to understand that here we're crossing into this sort of neverland of mathematics, which is sort of mathematicians started to believe that whatever they write, if it doesn't lead to contradictions, exists. Sort of like if I say that the fact that there is a roasted pig in my refrigerator doesn't lead to contradiction, which it doesn't, implies there is a roasted pig in my refrigerator. I wish the logic worked, but that's modern mathematics too. So you could get into really big sets. This mechanism, sort of the moment you open set theory, it leads not just to true infinities, but some unreachable infinities. And what do they mean? Again, do you encounter them? Oh, well, guys, no. This is the good news. But they are part of the set theory. However, before we could go further, there was a guy called Bertrand Russell, Lord Russell, a fascinating figure, the guy who wrote very many books on every subject under the sun, from sex to politics. And as he himself remarked, sadly enough, his name will be remembered because of the stupid paradox, and, which is sadly enough true. That is, nobody reads him anymore. But he observed that he could shorten the Cantor's proof. Remember the proof? And the proof was to take things which are not members of the image. He says, why bother? Let's take all sets and then take the subset of all sets, which are sets which do not contain themselves. We could write it like that. And so there is a set like that. Now the question is this set a member of itself? Tough. If it is, it isn't. If it isn't, it is. It's a paradox. And the world froze. Sort of. By the way, it's not clear whether Russell invented it, because there's clear evidence that Zermelo invented it at least a year before. But it doesn't matter. Zermelo told Hilbert about it, but he didn't publish. Russell published. So, by the normal laws, Russell paradox. But it's very obvious that something bad, we have a theory which allows you to get to the contradictions. People were shocked. You cannot imagine. That was viewed as that all of the mathematics was in danger, which is paradoxical, because there was no set theory just the other day. And mathematics was doing just fine. They invent set theory, then there is this paradox, and mathematics is in danger. It wasn't in any danger. People were, sort of bridges were not collapsing. Planes were flying, barely at that time, but they were. The artillery was very well sort of designed. You could shoot a ship from 20-mile distance, with the help of mathematics. Everything worked. But there was a sense of doom, truly sense of doom. Like Frege writes down to one of his friends, it is all over. It is just all over. It repeats itself, by the way. When Gödel gives a talk on his theorem, von Neumann is in the audience. And von Neumann gets out of the room and he says, it's all over. Well, apparently we're still around. So I think that the demise of mathematics was much exaggerated, but there was a sense of crisis. And there were multiple attempts. The first sort of attempt, and people thought the winning attempt, was the attempt by Russell and Whitehead to write their monumental work Principia Mathematica, where they would prove everything strictly and avoid paradoxes with the help of a ramified theory of types. And you don't need to know what it is, because as far as we know, only one person ever read the work, that being Kurt Gödel. It's not readable, and it possesses some remarkable properties. It takes 222 pages to prove that 2 + 2 is 4. So, it's just not a workable thing. It might contain some wisdom, but since it's 3 incomprehensive volume they use Peano notation, which they improve, it didn't work. So the way which worked was a work by Zermelo, who at that time was in Göttingen working with Hilbert, who decided to come up with the axiomatic set theory with a bunch of axioms which would guarantee that there are no paradoxes. And he came up with 7 axioms. All of them are comprehensible. So observe that now nobody uses Zermelo axioms. Everybody uses Zermelo-Frankel axioms. They are not comprehensible. That is, Zermelo part is comprehensible. I'll explain. Let me finish next time, because otherwise I'll rush it. I think I will restart Zermelo axioms the next time, okay? Because they're important. Because if as a result of our activities you will know Peano axioms and Zermelo axioms, my effort is not utterly in vain, only partially. Thank you.